A woman buys a calculator. She owns it. It sits in her drawer. She never has to ask anyone's permission to use it. Across town, a man picks up the phone, calls a service, and asks someone else to do the calculation for him. He never sees the machine that does the work. He just gets the answer back. Same question, same arithmetic. Two completely different worlds. One of those worlds is called local. The other is called cloud. And underneath both of them sits the same strange object, a brain made entirely of numbers, packed into a single file, read by an engine that produces one word at a time. Today, we open that file. We take the machine apart, piece by piece, until there's nothing left to explain. This is Narrator, Analyst, Practitioner, Scholar, Channel. I'm the narrator. I hold the thread, ask the questions, and keep the conversation grounded. With me are three voices who are going to take apart something almost everyone uses now, and almost no one has actually looked inside. Let me bring them in.
I'm the scholar. My work sits at the intersection of the history of computation and the philosophy of what a model even is, why we reach for human metaphors like brains and vision and language to describe machines that work nothing like us. Today, we're tracing an idea from a simple analogy all the way down to a single number being multiplied on a chip, and I find that whole descent worth taking slowly.
I'm the practitioner. I've spent years actually running these things, downloading models, running out of random access memory, choosing the wrong quantization, waiting for a context window to fill up. The scholar works with ideas. I work with what happens when your laptop fan starts screaming at 2 in the morning. And on the best days, those two things line up perfectly.
And I'm the analyst. I look at this as a system, inputs, layers, formats, hardware, outputs, and whether the architecture actually holds together end to end. Today, we're going from a human versus artificial intelligence analogy through local models and cloud models, through the apps and engines that run them, all the way down to how a single token gets predicted. In order, nothing skipped.
4 perspectives, 1 machine, and a question worth sitting with before we even start moving. When you type a sentence into an artificial intelligence and a reply appears, what precisely just happened? Let's find out. Part 1, the analogy, why we compare artificial intelligence models to humans. Scholar, every explanation of artificial intelligence we will try to start with a comparison to a human being. Vision, hearing, speech, language. How can we relate?
It comes from necessity, not accuracy. A human being has vision ability, hearing ability, speaking ability, language ability, a small set of faculties we understand intuitively because we live inside them. Artificial intelligence models are built the same way, functionally separate systems for image generation, for speech and audio, for vision, and for language. And language models split further into smaller language models and large language models, the LLM. The analogy maps one structure onto another, but it is only an analogy, not a technical equivalence.
That caveat matters more than people give it credit for. The word large in large language model refers to scale, the size of the model and the size of its training. It is not a claim about intelligence, and it's not a claim that humans and artificial intelligence learn or think the same way. The analogy compares functions, not mechanisms.
Where it actually earns its keep is in explaining capability, not cognition. Think of two people. Person A has a narrower vocabulary, less language experience, fewer language tasks under their belt. Person B has a broader vocabulary, more experience, more varied tasks. Person B's broader language capability is the analogy for a large language model. Not because the model knows more the way a well-read person does, but because, functionally, it can handle a wider range of language work.
So the full picture, zoomed out, image generation models, speech and audio models, vision models, language models splitting into smaller and large, and one more branch we haven't named yet.
Multimodal models, systems that combine more than one of those senses at once, text plus image plus audio in a single model. That's the complete hierarchy. And everything we talk about for the rest of this episode leaves somewhere inside that tree.
Part 2, Local versus Cloud, the calculator analogy. Let's move to the question underneath almost every decision people make about artificial intelligence. Do you run the model yourself, or does someone else run it for you?
The easiest way I've ever found to explain this, imagine you want a calculator. Option 1, you buy the calculator, it's yours. You can use it whenever you want. Your calculations stay at home, on your own desk. The trade-off is you're the one maintaining it, paying for the hardware, keeping it running. Option 2, you don't buy anything. You call a very powerful calculator service whenever you need it. You don't own it, you pay to use it, and their infrastructure does all the work.
Translate that into the actual workflow, and it holds up cleanly. A local model, you download it, and you run it on your own computer. No API request is necessarily required. 4 steps and you're self-contained. A cloud model, you choose a model from a service, your request travels to that provider, the provider runs the model on their infrastructure, and the response comes back to you.
And inside that local path, there's a small hierarchy worth naming, because it explains everything that follows this episode. An artificial intelligence model splits into an image model and a language model. The language model becomes, at scale, a large language model. That large language model is represented by its learned parameters, commonly called model weights. Those weights can be packaged into a model file format such as GGUF for efficient storage and loading. That format gets loaded by an inference engine or runtime llama.cpp is the standard example. That runtime runs on hardware CPU, GPU, RAM, and out the other end output. Every single term we use for the rest of this conversation is a link in that one chain.
Model, weights, format, engine, hardware, output. Hold onto that chain. We're going to walk it slowly, several times, from several directions. Part 3, Local versus Cloud, the full comparison. Now put the two side by side properly. Where does a local model actually differ from a cloud model, category by category?
Start with where it runs. Local runs on your computer. Cloud runs on the provider's servers. Internet for local, often not required after setup. For cloud, generally required full stop. Your own random access memory and GPU, very important for local. Much less important for cloud, because you're borrowing someone else's.
Model size is where this gets real fast. A local model is usually constrained by whatever hardware is sitting on your desk. A cloud model can be extremely large because you're never the one loading it into memory. Speed depends on your PC locally, depends on the provider and the network in the cloud. And privacy, this is the one people care about most. Local can keep data entirely on your machine. Cloud sends your data to the service, to the API.
Cost flips the trade-off around. Local cost is hardware and electricity, a one-time sunk investment. Cloud cost is usually an ongoing API or subscription fee. Setup is more technical locally. You're downloading and updating the model yourself. Setup is usually easier in the cloud. The provider manages it for you. And that trade-off, more control versus less infrastructure burden, is really just the buy versus rent decision, dressed up in GPUs instead of appliances.
One more row worth saying out loud.
offline use. Local, yes. Cloud, generally no. That single row is often the whole decision for someone choosing between the two.
Part 4, the apps and the ecosystem. So, you've chosen local. But what are you actually opening on your screen to make all of this happen?
There are two basic shapes of application, and they behave very differently. The first is a desktop graphical user interface app. It's installed directly on your computer. It runs locally. It can work offline, and it can interact much more deeply with your computer's hardware. LM Studio and GPT-4 all are examples of this kind of application. The second shape is a web app. You usually open it through a browser. It is built around web technologies and may depend on a server or an internet connection. And because it lives inside the browser, its access to your computer's hardware is generally more restricted. Google Docs is a familiar example of this shape.
Now, underneath the desktop AI application, there is an entire ecosystem, a collection of tools, each solving a slightly different part of the same problem. Let's look at a few of them. LM Studio is a desktop graphical user interface app for discovering, downloading, and running local models. GPT-4 All is a desktop local artificial intelligence application with document interaction and retrieval augmented generation features built in. Ollama is a local model runner designed to run models on your computer and expose them through an API. Jan is an open-source chat GPT-like desktop application for running artificial intelligence locally. Anything LLM is built around local artificial intelligence, documents, RAG, and workspaces. And then there is Open Web UI, a web-based interface that can connect to local models and give you a browser-based experience.
But now, we go one level deeper, because underneath some of these applications, there are the engines and frameworks that actually do much of the heavy lifting. llama.cpp is a major inference engine for running many language models locally. Cobalt.cpp packages local model inference with a user-friendly interface. Text Generation Web UI provides a more advanced interface for interacting with locally hosted models. Local AI provides a self-hosted API layer for local artificial intelligence models. vLLM is designed for high-performance model serving, particularly when you want to serve models efficiently at scale. And MLX, along with MLXLM, provides Apple's own machine learning framework and tools for running models efficiently on Apple hardware.
That's a long list of names. Is there a pattern underneath all of it?
There is, and it's the whole point of naming them together. Some of these are things you actually open. You see a window, you click buttons, you download a model, you type a prompt. Those are the applications and interfaces. The rest are things running underneath. You may never see them directly. They are the runtimes, inference engines, servers, APIs, or frameworks that help the model actually run.
And once you learn to put each name into the right bucket, application, interface, runtime, engine, framework, the ecosystem stops feeling like a wall of unrelated tools. You start seeing the architecture underneath them instead. Some things you open, some things run underneath, and together they form the local AI ecosystem.
Part 5, GPT-4 All versus LM Studio, 8. Working example. Let's see an example comparing GPT-4 All and LM Studio desktop graphical user interface apps.
Feature for feature, they're closer than people expect. Both run models locally, both let you download models, both have a chat interface, both support local documents and retrieval augmented generation, both work offline, both expose a local API. The difference is less about capability and more about polish, workflow, and which community you land in.
So walk through what actually happens end to end, using GPT-4All as the example, because this sequence is identical no matter which app you pick. Step 1, you ask a question. Explain gravity. Step 2, the application Let's see for GPT-4All application receives that request. Step 3, llama.cpp, the inference engine processes the request. Step 4, it uses the selected artificial intelligence model, QN, Llama, Mistral, whichever one you've loaded. We will see in detail few of the artificial intelligence models coming up now after this part. Step 5, your CPU or GPU performs the heavy calculations. Step 6, you get the answer.
Ask, receive, process, select the model, compute, answer. 6 steps. Remember that shape for now. It's going to reappear in more detail before this episode ends, and it will make more sense later. Part 6, the models you can actually download. Let's open the model itself. When someone downloads a local LLM, what are they actually choosing between?
A handful of terms that sound technical but map onto something simple. The model is the AI, brain. Quantization is compression of that brain. Random access memory requirement is how much memory your computer needs to operate it. File size is how much storage the model occupies on disk. And models differ from each other along 5 lines: capability, and how well they reason and follow instructions, how much context and knowledge they can hold, how fast they respond, how well they suit documents and retrieval-augmented generation, and whether they're specialized for a particular language.
Put numbers on it. News Hermes 2. Mistral DPO 7 billion parameters, Q40 quantization, about 3.8 gigabytes, 8 gigabytes of random access memory required, and it's built as a fast chat and instruction model. Llama 3.18b instruct, 8 billion parameters, roughly 4.3 gigabytes, also 8 gigabytes of random access memory, but with a standout feature, a 128K context window, meaning it's built for large, general-purpose work. Mistral Instruct and Mistral Open Orca sit in the same class, 7 billion parameters, around 3.8 gigabytes, 8 gigabytes of random access memory, both optimized for fast instruction following and chat.
And those numbers aren't trivia, they are the actual purchasing decision. 7B and 8B refer to roughly how many parameters are in the neural network. 7 billion, 8 billion. Q40 means 4-bit quantization, which compresses the model enough to run on a normal computer with far less random access memory than the full version would need. That 128K context on Llama 3.1 particularly matters. It lets the model hold a very large amount of text in a single conversation, which is exactly what you want for large legal documents, books, research material, or case files. The takeaway is simple. Pick the model based on your random access memory, your storage, and what you actually need it for. Chat speed, long documents, or general-purpose use.
And that's before we even get to the earlier generation models still in circulation.
Established local models, earlier generation systems that remain available and usable in apps like GPT-4All. Falcon, 7 billion parameters, 3.9 gigabytes, 8 gigabytes of random access memory, instruction-based and very fast. Orca 2, full version, 13 billion parameters, 6.9 gigabytes, 16 gigabytes of random access memory. A larger Llama 2-based instruction model. Orca 2 Medium, the lightweight version, 7 billion parameters, only 6 gigabytes. Wizard V1.2, also 13 billion parameters, 6.9 gigabytes, 16 gigabytes of random access memory, designed specifically to produce longer responses.
4 short conclusions from that table, and they're worth stating precisely. Orca 2 Full and Wizard v1.2 are both 13B models, requiring roughly 16 gigabytes of random access memory compared to the 8 gigabytes the 7B and 8B models need. Falcon is primarily about speed. The description explicitly emphasizes very fast and fastest responses. Orca 2 Medium is the lightweight version, 7B, only 3.6 gigabytes, sitting in the same practical hardware class as the other 7B models, powerful without heavy hardware. And Wizard v1.2 is designed to produce longer responses, which doesn't automatically mean it's more intelligent. Long answers and better reasoning are different things.
Part 7, the powerful models running today. That was in GPT-4all, which were just amazing. We will look more of those in a while. For now, let us look into what does the frontier of local models actually look like, inside an app like LM Studio.
Few examples, all available in LM Studio right now. Bonsai 27B, from Prism ML's family of binary and ternary QN3. 6 models, built to retain strong reasoning, coding, and agentic capability at an extremely small footprint. Binary weights compress the model to about 3.9 gigabytes, bringing 27B-class reasoning to a phone-class footprint. Across 15 thinking mode benchmarks, the binary version retains 89.5% of the full precision average score, and the ternary version retains 94.6%. It supports vision, tool use, hybrid thinking, and a 262K token context window.
Then Gemma 4 from Google DeepMind, few of them. Gemma 412B, QAT, a quantization-aware training version designed to keep quality close to full precision while using far less memory to load. Gemma 426B A4B, QAT, the same quantization-aware approach, but on an efficient architecture built for scalable local deployment. Gemma 412B Unified, notable because it skips separate encoders entirely, projecting image patches directly into the language model's embedding space through lightweight linear layers, so every modality feeds into a single decoder-only transformer. It supports a 256K token context window with vision built in.
Across the Gemma 4 family, 7 capabilities repeat, reasoning across all models with configurable thinking modes, multimodal processing of text and image with variable resolution, dense and mixture of experts architectures for different deployment scales, on-device optimization with 128K context on the small models and 256K on the medium ones. A genuinely useful jump in coding and agentic function calling, and native system role support for more structured conversations. And sitting alongside all of that, Nematron 3 Nano 4B from NVIDIA, a general-purpose reasoning and chat model compressed from Nematron Nano 9B V2, 4 billion parameters in a hybrid Mamba 2 transformer architecture. With a reasoning toggle you can switch on or off, native agentic and tool use support, and a 256K token context window.
Before we go to artificial intelligence inference stack, engines, and formats, here are a few models available in GPT-4all which I would like to discuss as well. Reasoner v1, the DeepSeek Distills, and Llama 3. Let's put 4 specific models on the table at once and compare them the way you actually would before downloading one.
4 columns. Reasoner v1, DeepSeek 1 Distill QN7B, Llama 3. 8B Instruct, and DeepSeek 1 Distill QN14B. Start with what each one actually is. Reasoner v1 is based on QN 2.5 coder 7B with a built-in JavaScript code interpreter built for complex reasoning tasks that benefit from computational analysis. It's released under the Apache License 2.0, and it's tagged for reasoning. DeepSeekR 1DistillQN7B is the official QN 2.5 Math 7B distillation of DeepSeekR 1, released under the MIT license, with no restrictions on commercial use, also tagged for reasoning. Llama 3 8B Instruct is a fast, chat-based model, trained by Meta, that accepts system prompts in the Llama 3 format, released under the Meta Llama 3 community license. And DeepSeekR 1DistillQN14B is the official QN 2.5-14B distillation of DeepSeekR 1, same MIT license, same unrestricted commercial use, also tagged for reasoning, just built on a bigger base.
Now the numbers that actually decide whether it runs on your machine. Reasoner V1, 4.13 gigabytes, 8 gigabytes of random access memory, 8 billion parameters. DeepSeekR 1DistillQN7B, 4.14 gigabytes, 8 gigabytes of random access memory, 7 billion parameters. Llama 3 8B Instruct, 4.34 gigabytes, 8 gigabytes of random access memory, 8 billion parameters. And DeepSeekR 1DistillQN14B, 7.96 gigabytes, and here's the jump, 16 gigabytes of random access memory. Because it's carrying 14 billion parameters, 3 of these sit comfortably in the same 8 gigabyte class. The fourth doubles the requirement because it's roughly double the size.
And underneath all 4, the quantization is identical, Q40 across the board. Same compression method, same trade-off between size and quality, applied consistently. What differs is the type, the underlying architecture family each one is built from. Reasoner V1 is QN2. Both distills are DeepSeek. Llama 3 8B Instruct is unsurprisingly Llama 3, so the actual decision hiding inside this table isn't really about which model is best. It's 3 models in the same weight class, Reasoner V1, the 7B DeepSeek Distill, and Llama 3 8B, each suited to a slightly different job. Code and computation, math-flavored reasoning, fast general chat. And then one model that steps outside that class entirely, the 14B Distill, trading double the random access memory for meaningfully more reasoning capacity. The table isn't ranking them, it's letting you match the job to the machine.
Few more models, from 8 billion parameters down to 1. One more table, 4 more models, and this one comes with something the others didn't. 8. Built-in decision guide, running from maximum capability down to minimum hardware.
4 columns, and this time they are arranged deliberately largest to smallest. DeepSeekR 1Distill Llama 8B, Llama 3.23B Instruct, DeepSeekR 1Distill QN 1.5B, and Llama 3.21B Instruct. DeepSeekR 1Distill Llama 8B is the official Llama 3.1-8B distillation of DeepSeekR 1 reasoning capable, no restrictions on commercial use, released under MIT. Llama 3.23B Instruct is a fast, instruct-tuned, multilingual chat model, agentic system capable, trained by Meta, released under the Meta Llama 3.2 community license. DeepSeekR 1, Distill QN 1.5, B is the official QN 2.5, Math 1.5B distillation of DeepSeekR 1, also reasoning capable, also unrestricted for commercial use, also MIT. And Llama 3.21B Instruct, the smallest of the 4, fast, instruct-tuned, multilingual, agentic capable, trained by Meta, same community license as its 3B sibling.
Now the hardware math, and this is where the spread really opens up. DeepSeekR 1Distill Llama 8B, 4.35 gigabytes, 8 gigabytes of random access memory, 8 billion parameters. Llama 3.23B Instruct, 1.79 gigabytes, 4 gigabytes of random access memory, 3 billion parameters. DeepSeek R1 Distill QN 1.5B, roughly 1.02 gigabytes, 3 gigabytes of random access memory, 1.5 billion parameters, and Llama 3.21b Instruct, just 737 megabytes, 2 gigabytes of RAM, 1 billion parameters. Same quantization throughout, Q40 across all four. 2 model families alternating DeepSeek, llama 3, DeepSeek, llama 3, and licensing that follows the family, MIT for the DeepSeek distills, Meta's community license for both llama models.
What makes this table different from a plain spec sheet is the guide sitting underneath it. 4 lanes, each solving for a different priority. Maximum reasoning, DeepSeek R1 Distill Llama 8B, the largest model, with the full 8 billion parameters. Balance of performance and resources, Llama 3.23b Instruct, 3 billion parameters, running on only about 4 gigabytes of random access memory. Lightweight reasoning, DeepSeek R1 Distill QN 1.5b, a genuine reasoning model, just compressed into a much smaller footprint. And lowest hardware requirement, Llama 3.21b Instruct, needing only around 2 gigabytes of random access memory.
And that bottom bar makes the entire trade-off visible in a single line. 8B down to 3B down to 1.5B down to 1B, more capability on one end, less hardware required on the other. It's not that one model is better than the rest. It's the same underlying reasoning ability, poured into 4 different container sizes, and the right one is whichever size actually fits the machine you're holding it in.
Part 8, the engines behind the models. Every model we've just named still needs something to actually run it. That's the inference stack, the engines and formats underneath the apps.
Here are a few of the names we will discuss. llama.cpp, a C++ inference engine for LLMs, lightweight and fast, best for CPU inference and low memory use, with simplicity and efficiency as its core strength. vLLM, a high-performance LLM serving engine with continuous batching, best for high-throughput inference and server environments, built for speed and scalability. SGLang, a high-performance structured output and long-context engine, best for long-context, structured output, and retrieval-augmented generation workflows.
TensorRT-LLM, NVIDIA-owned optimized inference engine, best for NVIDIA GPUs where maximum performance is the goal. MLX, optimized specifically for Apple Silicon, best for Mac users who want fast local inference. Xllama and Xllama v2 are inference engines designed primarily for efficient inference, with compatible quantized model formats, particularly GPTQ and related formats. They should not be described as GGUF inference engines. Ollama, itself built on llama.cpp, a user-friendly interface, best for easy setup, local chat, and everyday productivity, with simplicity as its whole appeal.
And the honest advice underneath all 7 names, high-performance inference, is an application choice that deserves to actually be tested, not assumed. For CPUs and small models, reach for llama.cpp. For high throughput and servers, vLLM. For long context and structured output, SGLang. For maximum GPU performance, TensorRT-LLM. For Apple Silicon, MLX. For GGUF models, llama.cpp and compatible runtimes are common choices. Xllama v2 is primarily associated with GPTQ and other compatible quantized model formats. For the easiest local experience, Ollama. More options means more power, but only once you know which option actually matches your hardware.
Part 9, the cloud side, who's running what? We've spent a long time inside local machines. Let's cross back over to the cloud and look at who's actually offering what right now.
Before we look at the map, there's one very important warning. This is a snapshot of the model landscape as of the date of this episode. The cloud model landscape changes extremely fast. Providers introduce new models, upgrade existing ones, rename models, move models into different tiers, and discontinue older ones. So do not treat this board as a permanent or timeless map. What you're seeing here represents the landscape as discussed in this episode at this point in time. With that firmly in mind, let's look at the providers. OpenAI's standard tier runs GPT 5.6 Sol, Terra, and Luna, alongside GPT 5.5, GPT 5.4, GPT 5.4 Mini, and Nano, with GPT 5.5 Pro and GPT 5.4 Pro as premium options. DeepSeek offers DeepSeek V4 Flash as the fast, cost-efficient option, with V4 Pro as its premium, advanced reasoning model. Google Gemini spans Gemini 3.6 Flash, 3.5 Flashlight, and 3.5 Flash as standard options, with Gemini 3.1 Pro as the premium, most capable tier. Grok offers Grok 4.1 Fast as its standard option and Grok 4.5 as its most advanced flagship. Perplexity runs its Sonar family, Sonar for fast search, Sonar Pro as the premium option, and Sonar Reasoning Pro and Sonar Deep Research as specialized tools for deeper, long-form research.
On the other half of the board, Anthropic's Claude runs Claude Haiku 4.5 as the fast and efficient standard option, with Claude Sonnet 5 and Claude Opus 4.8 as premium, high performance, and most capable tiers respectively. Mistral AI spans Mistral Small 4, Medium 3.5, and Large 3 as standard models, with DevStral 2 for coding and agentic tool use, and Leanstral 1.5 for formal reasoning and proofs as specialized premium options. Kimi offers Kimi K2.5 as a balanced and versatile model, with K2.6 as its most advanced 256K context, multimodal and agentic premium tier. Meta's Llama runs Llama 4 Scout as the efficient, long context option, and Llama 4 Maverick as the high-performance multimodal flagship. And QN from Alibaba spans QN Flash and QN3 Coda Flash as standard options, with QN 3.7 Plus and QN 3.7 Max as premium tiers.
And what ties this entire board together is a simple 4-step loop, repeated across every one of these providers. You choose a model from a service. Your request goes to that provider. The provider runs the model on its own infrastructure, and you get the response back. So the fundamental pattern is simple. You choose, they run it. You get the result. Powerful models hosted by leading providers, with the important reminder that the specific models on this board can change at any time.
Part 10, what's actually inside the machine. We've now toured both sides, local and cloud, apps and engines, downloadable models and hosted ones. Let's go back underneath all of it to the pipeline itself.
One structure, 6 layers, and it's the same structure whether you're on a laptop or talking to a data center. An image model understands images. Language model understands text. Both feed into a large language model, which combines and understands at scale. The model is represented by its learned parameters or weights. GGUF file is a model file format that can package those weights together with metadata and other information needed by a compatible inference engine. Think of the weights as the learned parameters and GGUF as the package used to store and load them. An inference engine, like llama.cpp, loads and runs that format. Hardware, CPU, GPU, random access memory provides the actual computing power, and the output is the model's response.
6 stages you can literally watch happen in order every time you ask a local model anything. You, the user, ask a question or give a prompt. The application or front-end, GPT-4 or Ollama, whatever you're running, shows the interface, manages your chats and settings, and sends your request to the engine. The inference engine, llama.cpp, is where the actual magic happens. It loads the model, manages memory, runs the model layer by layer, and generates tokens one by one. The model's learned parameters are the core of what the model has learned. The GGUF file is the file format that packages those parameters, together with metadata and other information, so a compatible engine can load and run the model.
Then the compute backend, where all the math actually gets executed. CUDA for NVIDIA GPU, Metal for Apple Silicon, HIP for AMD GPU, Vulkan across various GPUs, Sickle for Intel GPUs, or plain CPU with BLAS and OpenMP if there's no GPU at all. And finally, hardware, your own machine's CPU, GPU, and NPU, physically powering every one of those computations. Ask, bridge, engine, brain, backend, hardware, and then the response travels all the way back to you. That loop is the entire story artificial intelligence, told once, cleanly.
Part 11, GGUF, the brain packaged. We keep returning to one word, GGUF. Let's actually open it.
GGUF doesn't have a universally agreed official full form. It's the name of a model file format created by Georgy Jurganov for the llama.cpp ecosystem, succeeding the older GGML format. What it is, functionally, is a modern file format for storing and loading large language models efficiently.
The cleanest way to picture it, a smart package containing everything needed to run an LLM locally. The model, the brain, goes in. It comes out the other side as a GGUF file, an all-in-one package. Llama.cpp, the engine, reads that package, and the model runs locally on your own hardware. GGUF makes loading models faster, easier, and more efficient.
And inside one GGUF file, 4 things added together. Model weights, the learned parameters of the model, represented by billions of numerical values. Metadata, the model's architecture, its tokenizer details, its context length, its special tokens. Quantization info, exactly how the weights were compressed to save memory, from Q2 up through Q8, where lower bits mean smaller size but slightly less quality. GGUF can also contain model-specific metadata and configuration information, such as architecture details, vocabulary information, and other parameters needed by compatible software. The exact contents depend on the model and the GGUF implementation.
Why does any of that matter in practice?
Faster loading, lower memory usage, smaller file size, especially with quantization, and better compatibility across tools. In short, GGUF is a model file format designed for efficient storage and loading of compatible language models. It can package model weights and associated metadata in a form that compatible inference software can load.
Part 12, the full pipeline, training, inference, and the backends. Let's zoom out one more time and lay the entire pipeline side by side, start to finish.
The AI model pipeline from model to answer, step by step. An image model and a language model feed into a large language model, which combines and reasons at scale. That LLM is defined by its model weights. the learned knowledge. Those weights can be packaged into a model format, such as GGUF, for efficient local storage and loading. A compatible inference engine or runtime then loads the model and performs inference. An inference engine or runtime llama.cpp loads and runs the model. Hardware CPU, GPU random access memory provides the computing power. And out comes the output, the model's response. Model, engine, hardware, 3 groupings, 1 pipeline.
And llama.cpp itself deserves its own definition because it's one of the major inference engines used to perform the computational work required to run compatible language models locally. It's an LLM inference engine written in C and C++. It takes a trained model, loads it, and performs the massive mathematical calculations required for inference, for generating text. And it runs almost everywhere: Windows, Linux, Mac OS, and Android.
Which raises the distinction that explains why none of this needed to happen live, in front of you, in real time. Training happens once by the model's creator. Massive data, text, code, images, feeds a neural network's architecture, which learns its weights by adjusting parameters, and the result is a trained model, saved to disk. That's the expensive one-time phase. Inference happens every time you use the model. Your prompt goes in, the trained model is loaded into memory, llama.cpp, the inference engine runs it, predicts the next token, one word or word piece at a time, and repeats that process until it produces your answer. 2 phases, 1 goal, better answers.
Inside that inference engine specifically, 6 steps happen every single time. Load the model, read the GGUF file, load its weights and metadata, tokenize, convert your text into numbers, manage memory, use RAM and VRAM efficiently for the KV cache, buffers, and tensors. Run the model's layers, the matrix multiplications, attention and feed-forward networks. Generate the next token, pick the most probable next piece of text. Repeat, add that token back into the context and go again until finished.
And underneath all 6 of those steps, llama.cpp talks to the actual silicon through a compute backend, choosing the best one available. CUDA for NVIDIA GPU, Metal for Apple Silicon M1, M2, M3 and onward, HIP for AMD GPU, Vulkan for cross-platform GPU support, Sickle for Intel GPUs, or plain CPU, using BLAS and OpenMP when there's no GPU at all. The big picture, in one line, from your prompt to the final answer you ask, llama.cpp is the engine, the GGUF. Model is the brain, the hardware is the muscle, and the answer is the result.
Part 13, Token by Token, how a response is actually born. Let's slow down to the smallest possible unit of this whole process, 1 token being generated in real time.
6 steps, and this is the loop that's actually running underneath every single reply you've ever gotten from a local model. Step 1, your prompt. Explain gravity simply. Step 2, tokenize. The text is broken into numbers, into tokens, a sequence like 101, 333, 876, and onward. Step 3, the model inside llama.cpp looks at that pattern and predicts the next token. Step 4, the next token, a word piece, comes out as a number, say 4721. The model predicts the next token as a token ID. That ID is then decoded using the model's tokenizer into the corresponding token, which may be a whole word, part of a word, punctuation, or another token. Step 5, repeat to generate more. Step 6, the final answer. Gravity is a force that pulls objects toward each other, and that loop runs over and over, 10 times, 50 times, 1,000 times or more, until the answer is complete.
Which is exactly why quantization matters so much in practice. It's the dial that decides whether that loop runs at all on your machine. FP16 or FP32 is the highest quality and the largest size. Q80 or Q8K high quality smaller. Q5KM, a good balance of size and quality. Lower bit quantization generally reduces model size and memory requirements, while potentially introducing some loss in model quality. The actual quality and performance trade-off depends on the model, quantization method, and workload. Lower bits mean smaller size, but slightly less quality. Every local deployment is, underneath it, a negotiation along that exact scales.
And one more resource is spent silently in the background of every one of those tokens' memory. Model size sits on disk. It gets loaded into RAM or VRAM. That memory is split between the model weights themselves, the KV cache, buffers, and the runtime. And all of that is bounded by the context window, 4K, 8K, 16K, 32K, 128K tokens or more. More context means more memory used. That trade-off never goes away. It just moves, depending on which model and which engine you've chosen.
Part 14, Important Keynotes and Closing. We've gone from a human versus artificial intelligence analogy all the way down to a single predicted token. Let's bring it back up to the surface.
5 things worth actually remembering. The model, the GGUF file, is the brain, the knowledge. llama.cpp is the engine that runs that brain. The compute backends, CUDA, Metal, CPU. And the rest are how that engine actually uses your hardware. Different engines exist because different needs exist. A phone, a Mac, a server, and a bare CPU are not the same problem. And everything, the app, the engine, the format, the hardware, works together to turn your prompt into an answer.
If I had to compress the entire episode into one sentence, it would be this. The model knows, the engine runs, the hardware computes. As a simple metaphor, the model provides the learned parameters, the engine runs the model, and the hardware performs the computation.
And underneath that one sentence sits everything we've walked through today, an analogy borrowed from human ability, a choice between owning the calculator and renting it, an ecosystem of apps built on a handful of shared engines, a file format that packages a brain into something portable, and a loop, running token by token, that never actually stops until the answer is whole.
So, finally, it was one prompt, a question typed, a file read, a number predicted, and then another, until a sentence stood where nothing had been a moment before.
The machine never gets faster than its weakest link. The RAM you have, the format you chose, the engine reading it.
And the metaphor never gets closer than an analogy, a brain that isn't a brain, a memory that isn't quite memory, borrowed words for something genuinely new.
The model knows, the engine runs, the hardware computes.
That's the machine. That's the episode.